Hi, so I'm a software engineer at EMBL Hamburg. We have a total of 3 beamlines and 4 end stations. And today I'm going to try to explain in broad terms how our data acquisition system looks like and how we do on-the-fly processing on the stream data from our detectors for a couple of types of experiments. So our most interesting, I'm not sure this works.
Okay, I think it's a focus problem. You just try and get away. I think we're not focused on this. If we focus on that, then if you do that.
Okay.
Is it okay? No? Yeah.
Yes. So our most interesting data acquisition devices are our X-ray detectors. We have at each end station DECTRIS detector, but we also have one PCR camera for imaging experiments. And we write the data straight to 1 petabyte BGFS storage, which has served us very well for over 5 years now. However, we are about to replace it very soon with a new one that has arrived, is in testing now, and the replacement is probably going to take place in the winter shutdown next year. The data is transferred over 40 gigabit InfiniBand, and for processing we use a cluster of 13 servers, 13 nodes, each of which having 88 cores. In addition, for every detector, we have a dedicated server, one or more, that take the data out of the detector machine and do on-the-fly processing. And in terms of software, the main components are a GUI, a Becquerel in the case of SAXS, MXCuBE in the case of imaging and crystallography. We have a number of middle layer servers, and for an image display, we use ADXV. In the Monday talk of Soleil, I saw ADXV listed under diffraction software. We use ADXV for all types of experiments, crystallography, imaging, SAXS, so not limited to crystallography. We have at each end station an EIGER detector. P14 and P13 are our crystallography beamlines. TREXX is our time result crystallography, and P12 is our SAXS beamline. And P12 uses one of those 2 detectors a couple of times a year. In addition, we have at P14 on the same detector stage a PCR camera that's used for imaging experiments. Now, I didn't want to stay behind and also wanted to show you a formula. Probably some of you will recognize the Mach number. The Mach number is equal to the velocity of an object divided by the speed of sound. And at sea level, Mach 1 is equal to approximately 1,116 feet per second, where feet per second is an American unit for speed. And what does that have to do with data acquisition? Well, in data acquisition, we also deal with FPS, but in our case, this means frames per second and not feet per second. So we define Mach for data acquisition to mean the frames acquired by the detector, transferred, analyzed with the results displayed, and dumped to disk. And using this definition of Mach, we reached it in November of last year at P14 with the EIGER2 detector running in ROY mode in a collection of 100,000 frames. So this is a log file of how that famous Mach run looked like. We have here a column in the middle that shows the transfer speed. On the right, the first column is the frame count, frames transferred from the detector to the data receiving machine. And the last column is how many frames were actually processed and dumped to disk. And initially, the last column is lagging a little bit behind, which shows how much of a lag our BGFS has initially, and therefore how many frames we're buffering in memory. But as the collection progresses, they kind of, the last two columns start to match. And just below 60,000 frames, we reach Mach. And we stay at that till the end of the 100,000 frame collection. So we didn't do this Mach experiment for fun. We actually had a user, Kirill Kovalov, who was having a very interesting project investigating the rapid structural changes in rhodopsin. So he needed a kilohertz collection. And we did that at P14 with the 196 core setup. And what we see here in MXCuBE is the estimate of the resolution for each crystal as it is being hit by the beam. So this whole experiment finished in about 40 minutes. This particular collection was 300,000 frames, and the rest were somewhat similar in size. What's behind what the user sees? It's a collection of daemons. The detector server talks directly to the detector and controls the several devices that involved in the data acquisition. Thus, it's nicknamed the control freak daemon. The image tracker is the server that's sitting behind ADXV. And what it does is it follows in real time what frames are written to disk, and then makes requests to ADXV to display those frames from disk. And it makes those decisions based on how much diffraction there is in the image. It sorts frames by the highest diffraction and asks ADXV to display the frames with the best diffraction. Now, going to Tioga. Tioga is the server that receives the data from the detector. It decompresses it, does DOZOR analysis on each frame, where DOZOR is a program written by Gleb Burenkov and Sasha Popov for finding spots, let's say. Then Tioga writes a CBF file for MX, a T file for SAXS in memory. It compresses via zlib compression in memory the CBFs. And then on separate threads, it says user file ownership and permission on the files that are written to disk. And on separate threads, it writes those files to disk. And this last step here is needed because we actually run under different user accounts for every single user. So the input is the stream data via 0MQ from the detector. The output is images and compressed images and compressed spot files on disk. And the DOZOR results are exported via our TINA control system to interested clients. So we've had Tioga for about 5 years now. What changed with the arrival of the EIGER 2 was that we didn't have a computer to do everything in real time. So we needed more than one Tioga. And right now we have a setup where at P13 we have 2 Tioga machines, at P14 we have 3 for a total of 144 cores at P14. And once we got to the point where we were running with several Tiogas, we needed a server to aggregate the results that they produce. And in our case, this was Redon. What it does, it simply collects those results from the different Tiogas, and consolidates them together in real time and presents them to the clients. And I call it the impersonated daemon because it simply pretends it's a Tioga to clients, but it's nowhere close. And this is how the Redos and the Tiogas look in TINA, our control system. So what we see here is all the DOZOR results exported to clients. Those are just GUIs, standard GUIs, and they simply access the servers and ask for the results in which they're interested. And I hope this video works. So this is how running at maximum frame rate looks like. Oops, at P14. That maybe doesn't work. So what we have here is ADXV, MXCuBE, and the status of the detectors it is connecting, it's exposing now, and the frame rate of the transferring and processing of frames. So here is the resolution as it is calculated in real time. It finished very fast, faster than I could explain what was happening here. But this was in fact an 18,000 frame collection, and ADXV was displaying the whole time all the spots overlaid with the calculated by DOZOR spots on top. Now, this was the video was from P14, and this is TREXX, our time resolved station. So there was an experiment last week, and I just took a couple of screenshots. What we have here is again ADXV, MXCuBE, and a total of 5 ways of displaying the DOZOR results. 1, 2, 3, 4, and 5 with the overlays of the spots on ADXV. So this was halfway through the collection, and this was just before the end of the collection as it was happening. Now for imaging, because we were very happy with our crystallography setup, we have done something very similar using the same detector server, the same image tracker, and 2 new servers that write it specifically for imaging. And this is what the user sees during an imaging experiment. So the same MXCuBE, ADXV, is showing data, the raw images from BGFS, and an extension to MXCuBE, which shows flat field corrected frames. So the control goes from MXCuBE to the detector server to the PCO server, and the data is moving from the PCO camera to the PCO server, and from here it is zeroing to streamed to Arapaho, like a total parallel to the DECTRIS EIGER detector setup, where Arapaho starts writing TIFF files to disk, which are then displayed by ADXV on the commands coming from the image tracker. In parallel, Arapaho is doing flat field corrections on the frames and is sending them via TINE to MXCuBE for display. And this bug here that one sees is platinaris. And in a normal imaging experiment, we usually do 4 distances, a collection of 1800 frames per distance, which are preceded by between 30 and 100 empty frames for the flat field corrections. So in terms of time, how this looks like is the acquisition time is around 2.5 minutes, which includes the 4 distances with the detector moving before each subsequent collection. And what we added in the last few months was an actual reconstruction already at the beamline. The reconstruction consists of 2 parts, a CTF correction, which is doing a lot of forward and backward Fourier transforms, and the final reconstruction. And this whole acquisition plus reconstructions takes at the moment around 6 minutes. I did a quick test last week to see how it all behaves, and this is the log file of MXCuBE, but I did all the time calculations for you. What we have here is a raw file, and then a raw file as it is on disk. We have a CTF corrected image, and in those 2 we don't see anything practically. So that's the reason why we need a reconstruction very fast at the beamline to be really shown to the users. Right now, our reconstruction is about 20 times faster than what we had last year, and it is available at the Beamline with the sample snapshots being put at the end in ADXV as well. So this is kidney here that was being imaged, and as we see absolutely nothing in the first two images, in the final reconstruction we actually start seeing cells, which is what the users want to see. So I'm finishing. So in conclusion, with the system that we presented here, we allow for the instantaneous availability of frames for display and processing. Real-time analysis is happening in the control system, and we do it via DOZOR for crystallography, and we do flat field corrections for imaging. We immediately deliver processing results to the users. In the case of imaging, we still have a lot to improve, because those 3 minutes at the end that we have to wait for the reconstructions are still too long for us, and we want to make that even faster. And this was not what I was showing here. This was not a one-time setup, but what we have had at the Beamline for quite some time now, and it has been very stable and reliable. And as of recently, we're doing it also at rates of Mach 1. So with this, I would like to acknowledge everybody who was involved in this. I have been working mostly with Gleb Burankov, but for example, we have a new imaging group, little imaging group, consisting of Elizabeth Duke and Jonas Albers. And Ivar Skarpic has done a lot on the graphics there in MXCuBE. And with this, thank you.
Questions?
It's time for coffee.
I have one. Is you also doing zero crystallography? No?
At TREXX, yes. I'm not a scientist, I'm a software engineer.
Okay. Yes, yes, a question.
As a software engineer, is your source code available?
So in the case of Tioga, we actually gave it to Soleil, to the two Beamline scientists who are there, Martin Savko and I forgot the other person's name, but they have it, and from what I know, they have been using it in parallel with the file writer.
But it's not available on a repository and an open source license?
No, but I mean, if somebody wants to use it, they could just ask and we will give it to them.
I'd be interested in having the source code of DOZOR.
DOZOR, that's very much available. That is available, and Gleb and Sasha give it to everybody who asks, but it is in Fortran, so you have to understand what's happening.
They give the source code.
They
was given an executable.
They give both the executable and the source code.
Okay.
And Martin Savko for sure, and the other Beamline scientists at Soleil, they have also the source code.
It was a question I was thinking of asking everyone at the end of the talk. Is your source code custom source? We can do that under cost.
It's too much work for me to put it. We have our own internal SVN system, so for me it would be an extra effort to put everything online. But if somebody wants to use it in an SSK,
yeah, because we are moving towards open science, and then it's a request to the source code. Okay, thanks again.